despite this bombastic title, right, neutron skins and stars, the main subject of this talk is neutron skins. The problem is that I dig in the literature to find some beautiful things to say about neutron skins, and I could not find a history of neutron skins. Okay, so I think the history is being made right now. If you look at the textbooks and papers in the past, there's not so nice things to say about neutron skins because there were not much of thought about it in the past. So what I found, however,
About your microphone.
Oh, he was not in front of it. Now it's
yeah, however, if you go to Pygmy resonances, which is related, you're really gonna find some history. You see, it starts in 1961 with some first observation in gamma rays from Newton capture. Here's the reference. There was the first use of this name, Pygmy resonance, in 69. And then some people already started in 71 describing it in terms of collective excitation. And then there was a proposal in 1987 with the Kubono-san on J-Park about looking for this evidence for the existence of Pygmy resonances. So what people thought is that there should be, for example, in the electromagnetic response of nuclei, when you submit the nucleus to an electric magnetic field, you find the GDR here, and there should be a soft mode associated with something which would look like a vibration of a skin against the core. And you could look at the spectrum, find out if this was a signature of Pygmy resonance. That was the thing that people thought about. And then why is it relevant? Some people, and I talked to Gorielli about this, and he said, please forget this paper.
yeah.
And but I keep using it just as a motivation because you can see in the stars, if you have the absorption of energy during the explosion to excitation of the giant resonances, okay, you have an effect on the abundance. But if you include the Pygmy resonance, the effect goes in other directions. So it should have, in fact, I think this physically makes sense, even if he doesn't like his own paper. I do not know why, sincerely, he doesn't like his own paper. This is something that one might think about. It makes sense from the physical point of view that they might play a role in the stars in some ways. So how today we are discussing with some experimentalists, and the life of experimentalists is very hard. It's not like us in theory who can do neutron stars and use all sorts of inventions that we have in theory. And the only constraint we have are like masses, radially, and tidal deformation. While an experimentalist has data, he has a beam and a target, and then he puts the best detectors he can. But he cannot use all this imagination. People, yesterday, Liv Palm was discussing about breakup, and there were some people saying, well, we are still discussing about breakup. Well, that's what experimentalists measure, okay? There is not much else you can do with experiments. You cannot put a neutron star in the laboratory. You have a beam and a target, right? And we have to explain the experimental data. It's very easy to do neutron stars. Anybody can do neutron stars. You just put everything in a theory and you say, or another term in the Lagrangian, and you say, here's a Nature paper, I have found that it conducts better. So it's all, you know, now explain experiments. That's what we try to do. We need reactions. We need to understand the reactions. We talk a lot about the structure, the levels that we find, the diagonalization of all those matrices that we do to find where the levels are, the width of the levels and so on. But without this thing here, this is experimental, okay? Projectile, target, remember that. And we have to explain this before we explain what we find from the experiment. And we do this sort of thing. So we have to do reactions. We do the traditional thing at high energies. I will talk more about high energies here. And we have to use concepts such as relativity. Then we have to do with the continuum, we have to treat continuum in reaction theory. For example, in this paper here, these ingredients were included. And when you go to the continuum, you have to discretize states and do all that. Okay, and for example, here we have a thing which is really of interest. Because if you do all that, if you do the reaction theory part well, you can extract quantities like that. The response function, which is the initial function, final function, and some operator. The electromagnetic operator is easy, but you could have another thing there sandwiched. Now, here is data, for example, for lithium-11, okay? What the discussion was in, and it's still, I find it so funny, people are still discussing this. Is this a resonance, okay? And in this case, you can treat it with RPA, we can treat it whatever complex and continuum RPA that we use there. But in the end, you can find a way to explain this here, the long wave approximation, with a very simple formula. This comes from phase space. This comes from the response to this operator. And this is the excitation energy of the system. This is separation energy of the nucleon. If you have a two-body model, then this is what comes out in the long wavelength approximation. It has its imprint in RPA calculations to at low energies. So if you make a three-body model, you have a certain different response. And if you include finite state interactions, you see that it's relevant, okay? And you can explain experimental data. Now, there are people still discussing this kind of things. They use these formulas when they have experimental data, and they say the resonance is that there is no resonance here, okay? This is phase space, only phase space. As my friend Aaron Galosky used to say, so if you this measurement here, you have to start from zero, phase space, okay? And then you have to go to zero, because the photons here have a certain amount of energy. They cannot have that much of energy. And if you have zero at zero, you have to have a peak in the middle. And the peak is not a resonance. The peak is just a, there are still people who, and of course there are resonances in like nuclei, neutron-rich nuclei, we know that, but some of the things that we can explain with phase space only is true. So Maytal Duer, she's gonna give a talk later today, and she's gonna talk about the tetraneutron. There are some theorists who think that the tetraneutron, the resonance, is a phase space phenomenon. It's not a resonance. It's all open to discussion. We don't really know, because we know in neutron-rich nuclei, there are de facto resonances, not only phase space problems, right? Michael? Right? Yeah. Okay, so you can do all sorts of things. Nowadays, this is very popular, effective field theory, okay? And our effective field theory is something like that. You have a Lagrange, is a field theory, field theoretical thing, and you do Feynman diagrams. It's a completely different way to solve problems. And here was the first paper who did this hollow effective field theory by treating a nerd core and doing all these diagrams. And then you run into problems like you have to do regularization of integrals, you have to do renormalization by summing all the things. It's a completely different approach, but in the end, it should give the same result because the same physics encoded there. And you have this way to do things, and then you have to organize the contributions in powers like this. You have a large energy or large momentum, and you divide this from a low momentum, could be the masses of ion mass, for example. And then you use this theory to explain the same sort of results, and you get more or less the same thing with a band. Yes, go ahead.
Carlos, I always ask myself the question,
yeah.
Why? Because you can solve this problem, as you said, using many-body approach, even not that complicated many-body approach. Yes. So why would you like to do this using Halo EFT?
Well,
what are the intellectual gains through this exercise?
Well, I like it for the following reason. This approach is completely different with solving an equation with a potential, right? So you solve Feynman diagrams here, and it's beautiful from the point of view of beauty.
I'm asking about practicalities.
Well, they have, for example, if you look at some of the reactions like gamma deuteron going to proton plus neutron, Galton Rupak has done a famous paper in which Laura Marcucci in Pisa, they have analyzed a lot of reactions in sun, for example, with effective field theory and done much better than you can do. Okay, they have shown, they have a error quantification with the next to leading order, next to that we can't do with the Schrödinger equation. So practically, so of course you have, there is a limit for this theory. Okay, I always tell my friends, how do you handle Pauli principle with effective field theory? There's a way to Pauli principle, right? So you take a nerd core and then you do some sort of not really quantum field theory, because when you start including, for example, the Coulomb interaction, they included the same way we did in 1930s. Okay, so it's not really effective field theory anymore. So you are mixing things. It's not consistent anymore, especially when you have charged particles. And then when you have the many body problem and you have to treat Pauli principle, forget about it. Okay, so it's this effective field theory. Yeah, this effective field theory has a limitation. That's for sure with that. Yeah, sure. Okay, so hydrodynamic models treat nuclei as hydrodynamics, like a liquid. Okay, and you have different ways to see it, like in Gold-Habertella and Steinweder-Jensen mode. This is old stuff, and that's when Pygmy resonance showed up. People have used this long time ago to treat Pygmy resonance. You see Fanisaka, for example, worked on that. And then you get the response, the transition density. And here, for example, in this publication, I have tried to figure out with the parameters here to explain the position and the width of the Pygmy resonance. So this is old. Nowadays, it's more popular to use for heavier nuclear, medium to heavier nuclear density functionals. We have lots of parameters, right? This is the Sturm interaction. And what you want to find is the energy as a function of density, which is so-called the energy density functional. So this is a traditional approach which you use if you include pairing, then you have to treat either BCS, Hartree-Fock BCS, or Hartree-Fock Bogoliubov. This is something that which is in the market for many years, and we want to get those energy density functionals. And why we want that? Sorry, why we want that? Because we want to solve the equation for neutron stars to get diagrams like this: radius versus mass of neutron stars, distribution of neutron stars. And we want to get from the functional, because in order to solve this equation, we need one more, which is the energy density functional, to get the pressure, okay, to put it there. And what we do is we expand this around the saturation density, okay? This is an old story, how we do this, and we have been doing this for many years, okay? And there is also the dependence on the asymmetry of matter, how the nucleon and the proton density are different. And this is important because neutron stars mostly in newtons, one proton in 20 newtons, more or less. In fact, people don't know so well about this. Some people say it's in 100, some people say it's in 10. It's how many protons are in the neutron star. Anyway, we want to have this quantity here with the density of protons very small. And when you do that, you have the dependence of the pressure on this parameter here, which is the expansion parameter of the symmetry energy. Okay, the symmetry energy is this term here, which depends on the difference of the density of protons and neutrons. And you can again expand this in a Taylor series. And the first term is the bulk symmetry energy, and this is called the slope parameter, where x is the difference, is the deviation from the saturation density. Okay, so this guy here is crucial for explaining neutron matter, and different skirms give different values of this quantity. And in fact, you have like values up to 120 MeV, okay, in some skirm functionals. So it's very broad. So what we know barely is what happens around here for symmetric nuclear matter, neutrons equal protons. And what you want to do is to go here to explain neutron stars, right? So the equation is taken for asymmetric nuclear matter is very different. And we want to extrapolate to get there. Otherwise, you can never explain neutron stars. And now is the problem that close to the saturation density, everything seems to work well. Of course, all these terms and the relativistic density functionals work well here because you explain nuclei on Earth. But when you go to the stars, you have to go to higher densities or smaller densities, and they diverge. You see, this is shown in many contexts, right? So what people have seen is that if you have again this simple thing here, beam and target, okay?
Carlos.
Yes, you are interrupting me a lot. Okay. So in the end, I will have no time to finish my talk. Go ahead.
This is discussion, right?
Yes. Oh,
This is
time. Okay.
yes. This is part of the discussion time. You know, when you show the plot like this, okay, you create an impression that theories, you know, have all those terms, and you know they use them indiscriminately. But in fact, there is only one term functional, and all those differences, you know, which you show, they come from different calibration because those terms are fitted to different kind of data.
Right.
Okay, so there's only one term model, and there are different parameterizations.
Right.
And you know, some of those parameterizations are totally, you know, irrelevant to any problem we discuss.
Yeah, but I do not know which ones I through show out. Through show. I know you worked on this for 40 years, Witek. You have such an experience on this. But from all those functionals, I do not know which one should we throw out. They have to pass several tests. This is one test, if they can reproduce the masses and radii of neutron stars. But let me continue. Okay, so I think you're right. Well, so what people have done is, for example, if you look in this nucleus here and you look at the response function, you see a small peak in the Pygmy. But if you do, for example, Coulomb excitation, you enhance the low energy part, and you can see a peak, which in fact can be traced to what we call dipole polarizability. This is not the cross section for breakup. This is the cross section for real photo. This quantity here is called dipole polarizability, which in the end we can trace back to what we can get from experiments. Okay, and this in fact is shown here. These are experimental data. These peaks are enhanced. Okay, you can see that this would be the response, and this would be what happens during the experiment. Okay, because it enhances the low energy part of the. And then I go to Witek here. Witek and PG Reinhardt have done a lot of work on that, in fact. And here is just a small part of the work, not really making justice to all what they have done in statistics and correlations between dipole polarizability and other nuclear properties. But in this paper here, what was used is this idea that there is a correlation between dipole polarizability and neutron skin. So if you measure the dipole polarizability in Coulomb excitation experiments, then you have a handle on this quantity, which in the other direction will tell you about the neutron skin thickness. There we go. You started to talk about neutron skins now, right? We came from dipole resonances, Pygmy resonance. And in fact, this is some continuation of work that Xavier Rocamassa has done, and other people too, is a correlation between the neutron skin in several nuclei, in this case lead, with this low parameter. And you see that these are different energy density functionals, and I do not know which one I should throw away up to now. And what they have obtained in this experiment here, Tamirov, is this value here, okay? And some folks using effective field theories in Darmstadt, they have obtained a pretty close value. These are honest calculations, okay? They are not playing with numbers. They are trying to do as fair as they can with the physics, okay? And it comes pretty close, okay? Not so bad. Okay, so this is more or less a summary of what has been calculated and what has been measured with the dipole polarizability. If you want to know more, this is the paper. And there is also some interesting things. If you try to correlate the dipole polarizability directly with the skin, you see a scatter that you can pack together in a linear correlation when you multiply by the volume of the symmetry, volume term of the symmetry energy. This is something that Rocamassa has done, and we have redone this by looking at more energy functionals, and really this correlation exists, but it has to be plotted another way. And this is a slide I borrowed from WeTech, some talk that he gave. This person here has done calculations for neutron schemes and shown here in this graph for a large quantity of nuclei, okay? But if you look at the experimental data, and that's what Alexander is here and he's going after, you see it's very unpleasant situation in which these are experimental data obtained with antiprotons, okay? And you see for several nuclei there is some sort of linear correlation here. But my friend here, Sagal, and we have worked on that, and you can do whatever, you can use whatever sperm you want, okay? So what WeTech said that there is only one sperm, okay? Well, but I can play with those parameters to explain this, but I can use as many sperm because the data is so scattered that I cannot really use them to constrain which functional is better. And then we come to the case of the parity violation and electron scattering. What they have done is to look for this part here. Well, you cannot separate this part from everything else, which is the electromagnetic interaction. So you have the electromagnetic interaction, you have the weak interaction, the parity violating term, okay? And now whoever has worked with analyzing power, so you scatter electron with spin up and spin down, knows, if you are a theorist, you know that it's very hard to use a good theory to explain analyzing power. You have things that are subtle and nuanced, like off-shellness, okay, in the scattering. Although it's electromagnetic interaction, you still find it hard to explain. You can explain very well the cross sections, okay? But when you do analyzing power, it's very complicated. They audaciously went in that direction. They used this quantity here, looked for spin up and spin down scattering, and then you show that it depends on the form factor for the weak interaction, which is something that is associated with the weak charge in nuclei, and it's like what we know. This density here has to do with the charge density and also with the neutron proton density. The charge density, you have a size effect, and these are point particles with appropriate form factors. That's what they have done. And it was expected that this quantity here, this is again from Rocamassa, this quantity has a dependence on the neutron spin, okay? So in fact, this data here reflect this analysis here. And this analysis for me is highly, highly bad, okay? So of course they saw this, Nature and everything else, and people don't realize that what they are doing is an electron scattering, but it's not the electromagnetic part, okay? And besides, they do not have a form factor close to the origin. When it's close to the origin, you have a direct relationship with that, okay? But it's not so close to the origin. And then they have to use several different calculations like universal energy density functional or other functionals here, Lyon and so on. And it's extremely theory-based. So they are selling us something which is the best because it's electron scattering. It's not really electron scattering. It's just one point measured. Okay, somebody asked this yesterday. It's just one point. This point here is not even close to zero. And you have to pass through it a lot of functionals, and then you extract a number. This is the best number, by the way, for calcium 48, a number which is more or less what we expect. However, if you go to lead, they did the same thing. This is the result that they get after all this analysis, which they sell as being the greatest analysis in the world because it's electron scattering. It must be true, which is in fact not the case, okay? And then they get this number here, which nobody likes because it's too big, okay? And there must be a problem, okay? Well, I know what the problem is. The problem is that they try to, so as somebody said, they try to sell us something which is not really that great as people think, okay? Okay, so this is the situation now that we have. This is a compilation of a student, and we see here the different nuclei, and this band here are many density functionals. I do not know which one is the real one. WeTech knows what is the real one, okay? I don't know. And here is the Prex results. Alexander,
Just to comment on the data you were showing,
Yes.
error bars are only statistical.
There is no way that they could give systematic uncertainty on these numbers. And it's highly model dependent the way it is extracted. So
Right.
the comparison here, I mean, there is, and they tell it themselves.
Yeah, and I learned in the school when I was a teenager that errors always add. So if you would add the systematic errors here, this thing would blow up. Okay? Nope.
I don't want to interrupt.
Oh, you
But
already did.
Since you have this neutron skin and you have a point which is called Pyrex, okay, I don't think that we are supposed to call this Pyrex. Pyrex is APV, just one number at one Q value. This is something which was analyzed using various models, okay? So this is not a measurement from Pyrex. I just want to emphasize.
Yeah, but I think Alexandra has also a point that all these other data, they have systematic errors also, right, Alexandra, which is very hard. You are talking about the Prex only or the antiprotons also?
Highly model dependent.
Highly model dependent.
Everything is set on carbon 12 and they make the assumption of the density profile.
In order to get back to the, so this is a stretch that we discussed yesterday. If you want to get back to a neutron skin, you have to rely, and this is a two-particle Fermi distribution with two parameters for the neutrons, two parameters for the proton distributions, and then they fix this, and everything is normalized at some point on carbon 12. And also there was something which was not understood in the ratio for the proton and neutron annihilation. So, somehow there is a probability to annihilate with a proton and a neutron, and this is not exactly the same. And here there is a factor of 0.6, which depending on the analysis is taken or not taken. So
yes,
it's
and
really...
you remember there was a criticism yesterday to Rimanta's talk about this has been studied for so many years, so many decades in the past. Why are you doing this, Alexandra, again? The problem is this optical, anti-proton optical potential. In fact, if you could understand this better, we have to go back to problems which are unsolved. So they did this in the past, they didn't come out with anything. And basically his question was really mean, because what he was saying is there were so many smart people doing this in the past. Do you think we're smarter than they are? And they got nothing. We have to answer to him, yes, we are smarter than those guys. Otherwise, how can you sell that Lazarus is doing the right thing, which is what I was saying, which is to handle the most difficult problem, the anti-proton optical potential, because this is where the most systematic error is. Okay, so now when you move, and we have looked to the density functionals which are here in the middle, the best ones which fit here, okay, you cannot even say you can fit this thing, do not do a good job here. So the tests that we do for the energy density functionals, they work for something, they do not work for us. This is for the thin as a function of the neutron content. Okay, so we also have looked at the reaction part, the dynamics. If we have couple channels and we excite all these things, we have done this here, and we have found that very little changes are. We have that the experimental error has like 7% change, and we have found out that even I will not explain all this years the cross section. The experiment was done around here, and they are analyzed in terms of first order theory. When we go do a couple of channels, things change, but it cannot change the data. Okay. So recently there is a new proposal. We peel off neutrons from fragmentation reactions. You do fragmentation reactions and you get all these fragments. And the idea is basically the following. I sat in a bus with Hermann Fischbach for 3 hours. And he explained me that he had this student called Hauser. And Hauser had 4 years of work and didn't get anything done. So in a rainy weekend in Boston, I sat down and I put the angular momentum in the U and Y scope formulas. And then I showed that it started working, because the U and Y scope, they did everything, all these balance equations that you use for compound nucleus formation, But with the angular momentum, it works much better. However, the Hauser-Fischbach theory is statistical and has a lot of problems, because it's a lot of parameters there. It's not really pleasant to use Thales code and other things where you have parameters that you cannot explain, right? The transmissibilities and level densities. There's a lot of problems there. Oops, 10 minutes, okay? And so the idea was the following. You fragment and you look for all the fragments where you lose neutrons, okay? And you add all of them. So you know that this must be like a two-step reaction. You fragment, the fragment's excited and evaporates. And that's what you measure. When this guy's reaching the detector, it's after evaporation. In the evaporation part, if you want to do a theory to explain that, you use the statistical theory, Hauser-Feshbach theory. That's the only one we have, in fact, which is highly problematic. So in order to avoid that, you measure all the channels where neutrons are removed. So the cross-section, the primary fragments, before they evaporate, has by unitarity to be the same as after the evaporation, if you measure all neutron decay channels. Then we can do better, okay? Because we could use some Glauber theory to calculate the probability to remove the protons, to remove the neutrons, and this is better calculable than if you add to it the second step, which is the evaporation step. So that's the only thing we need. And in this calculation, what enters are the densities. And we can test densities. Now we have removal of charge, removal of neutrons, and you have excitation of giant resonance, which go through evaporation to usually neutron removal, okay, channels. Now this thing here is very peripheral and they go very forward. So what Tom says is that if we cut this with this detector, nylon here, the forward angles, we only have this part here, which comes from this. Okay, and now we can use this Glauber theory to calculate that. We have looked at some of this. We have published a paper in which we propose this together with Stefan Dipole, use some relativistic density functionals, and we have seen that the neutron skin is really sensitive, okay, to this slow parameter with different curves or different density functionals. And we have analyzed how this changes as a function, for example, along an isotopic chain, okay, and also the dependence on different L's. I'm going a little bit fast here because I want to finish. You can do proton targets, you can do also charge removal, and you can, that's the thing that the electron scattering experiment cannot do, and we can do. Okay, we can test along an isotopic chain. They can do with carbon 48, calcium 48, and let you wait. But we can do with hadrons. Of course, hadron is not as good as electron. Maybe, I don't really know. But you can test so many different things that you can pile up data, and then we can, in the end, perhaps say better than they will ever do with electron scattering. There are many things, and we have tested a lot of things here in the reaction theory, high order corrections of equianal, medium effects, and we have seen that when you have a carbon target, there is a difference. This is the excitation of giant resonance that we are really going to get out, but at high energies with the detector that I explained, with this as a function of energies, this is very good at high energies under control. That's what we think. This is one. There is, but a serious problem. What is the simplest experiment you can do in nuclear physics? It's a transmission experiment. You have a beam, and then on the other side of the target, you measure if the projectile is still there. This is called reaction cross-section, interaction cross-section. Look at carbon on carbon. This is carbon on carbon, put back to right here. We have this data and we have this data. If we do nuclear physics better, by including medium effects, okay, maybe polyblocking, we do worse. Why? We can explain better for the proton case. For the carbon case, we do worse. So you see where we are. We are still in this phase in which we have to look at the basic quantity in nuclear physics, the reaction cross-section, and try to figure out if you can do better theory to explain that, because you want to do what Tom Alma proposed. And here we have a compilation of several data, and we try to obtain these cross sections as a function of energy, for example. And you see that the data are so scattered, and there are even things that they don't really understand. This is for, it's hidden here behind. This is for charge changing cross sections that have been measured. You throw this on this, and you measure the different isotopes, the different elements that you have, charge changing cross sections. You have things that you don't really understand. So you have to make a better job, go back to the basics, beam, target, and transmission. I thought this would be a very simple experiment. They say, oh, it's not so easy. They have some experimentalists can explain. I think Alexander can explain. So we are trying to do that. These are all the data we could try to find and try to explain. You see that is highly unsatisfactory how we can explain this data. There are people who are proposing relativistic ion collisions in this paper here by using transport equations and trying, there is even a Trento interaction, okay? And looking at the correlation of neutron skin and some quantities associated with multiplicity of charged particles, okay? Try to extract this neutron skin. There was also a proposal that we never really explored much, which is this beautiful Maris polarization effect. It can be explained in a simple way. You have, it's a polarization thing too. You have a proton spin up, proton spin down. This is the whole wave function of the proton. It's a wave function. So sometimes parts of the wave function go through here and parts go through here. But through here, you have a longer meter path a longer path in the matter. Here we have a smaller, and the combination of spin interaction and the path along the matter through, for example, the spin orbit interaction makes asymmetries. And this can be simply explained in terms of the difference between spin up, and spin down, and spin up interactions has been beautifully explained in this paper here by Maris a long time ago, and it works beautifully. Okay, so this is this for oxygen 16. Okay, and you see how you can distinguish the two orbitals through this polarization effect. It's very hard to do this experiment because you need polarized with radioactive beams, you need polarized targets, okay? So Uesaka-san and others have tried to do this in Japan, and they have published a few papers. What we have proposed is that this quantity here is sensitive to the skin too. Okay, so it has a strong sensitivity, but Tom doesn't really want to do this. It's too complicated. Summary, I finished before my time, which is really great. We are trying to go from here to here. This is the playground of my theory friends. All of them nowadays like to work here because what I told you, it's much easier to work here than to explain experimental data, even elastic scattering or transmission cross sections. Okay, try to explain this from theory. But here you can do whatever you want with 10 to 57 nucleons. Now we also have a problem that we want to look at these properties of this small quantity, even a skin, which is such a small thing, and connect to the 10 to the 57 nucleons. Well, people might say you have been working 100 years with nuclear physics and you still didn't solve such simple problems like that. And the answer we have to them, my friends, we work the most difficult physics area in whole physics. Atoms are complicated. They are made of quarks and gluons. We don't really know the interaction so well. We will be working 100 years more in order to clarify a lot of aspects. And in solid state physics or in quantum optics, you work with electrons. I can do this in my spare time. Okay, try to do nuclear physics. If you think it's too easy, help us. Okay, because this what is the beauty of nuclear physics. I think. Well, about the best energy density functionals, I was thinking right when Wittek was talking. It's very easy to make a ranking of the most intelligent guy in the room. First ranking, Wittek Nazarevich. Second, anybody raise the hand? Well, now for the energy density functional, I don't see a way to take those functionals which explain different properties, quadrupole moments and other things, and eliminate them in order to, and it might be wrong because the one which explains better the mass radius relation and tidal deformability and neutron star mergers might do a good job, but when you go back to nuclear physics, doesn't do a good job. So it's a very tough problem that will take still a few years to solve. And I think that's what justifies all this simple work that we do in nuclear physics, but it's complicated to explain.
Thank you.
I'm a poet.
Yes.